In this video we'll be looking at the various types of convective system and convective weather associated with them that are possible. You can see there are two cumulonimbus clouds here and two cumulus clouds, and what's shown is their microphysical structure, so what phases of water they're made up of, and there's a number of lines indicated as well. Firstly, there's the convective condensation level, and that forms the cloud base of the convective clouds, and that's common to all. The second is the freezing level. That's the 0 degrees Celsius isotherm, shown here as a straight line. And below that, the clouds that consist of liquid water only. Between the freezing level and about minus 15 or minus 20 degrees Celsius, the clouds are a mixture of supercooled liquid water and ice crystals. It goes beyond the scope of thermodynamics to talk about the details, but in the real atmosphere, water does not freeze in its entirety at 0 degrees Celsius, and so there is what we get is known as mixed phased clouds. So there are two phases of water, supercooled liquid water and ice. Between minus 15 and minus 20 you get efficient ice crystal production, and above that you get more and more ice crystals and less supercooled liquid water, until above minus 40 degrees Celsius the cloud is consists entirely of ice crystals. So for a thunderstorm, you can see that there are various levels, and in particular you can see that the equilibrium level is going to be the tropopause, and you have an overshooting top. So the overshooting top is a product of the fact that for a large cape environment, parcels of air have momentum to overshoot the equilibrium level, which remember is also known as the level of zero buoyancy. So the overshooting parcels find themselves in a stable environment and collapse back down after time. The extended area above minus 40 is the cirriform anvil, so it's a region that consists entirely of ice. The region between minus 15 to about minus 20 is a region of very strong rates of formation of ice crystals, and if a cloud passes through about the minus 20 level, then you're going to see electrification. That's because large ice crystals falling through smaller ice crystals produces static electricity. The same thing that happens when you take your jumper off in winter or you brush your hair or whatever. So this particular thunderstorm on the left passes through that minus 20 degrees Celsius isotherm, and so there's electrification and lightning and thunderstorms of rain because there's that lightning and thunder, and an overshooting top and a cirriform anvil. The next thunderstorm show just pushes through that minus 20 degrees Celsius level, and so it's still a thunderstorm, it's still a cumulonimbus, but it has no anvil. Because of significant ice, though, it will appear as a glaciated top. The next two clouds are just cumulus clouds, and the first one is a mix of liquid water below the freezing level and supercooled liquid water. And the last cloud only extends to just below the freezing level, and so it's referred to as a warm cloud, which means that it only consists of liquid water. There's no supercooled liquid water. Now again, for reasons that go beyond the scope of the course, the greater the depth of cloud, the more likely it is that you're going to get showers of rain. And so if you only have a warm cloud, that is, there's no ice phase whatsoever, it's not nearly as certain that a shower will occur. Whereas if you have a cumulus cloud that extends through the freezing level, then it's more likely that you're going to get precipitation out of that. What we can also see, really, if you move right to left, is a sequence of development too. So every cumulonimbus cloud starts off as a shallow Q, which builds into a towering cumulus cloud, which is what the second cloud's referred to, and then a CB with a glaciated top, and then finally, if it gets deep enough, that with an overshooting top and a cirriform anvil. So here's a first example. It's from Sydney, and you can see that the maximum temperature is 25 degrees Celsius, and there's a surface dew point of 21, and that gives the resultant saturated adiabat for cloud parcels. There's a surface lifted index of minus 5, so there's a 5 degrees Celsius difference at 500 hectopascals between the parcels of air in the updraft and those in the environment, and that gives a CAPE of about 1500 joules per kilogram, which is quite reasonable, and a convective inhibition of 0 joules per kilogram, so this trace will convect for those values of temperature and dew point. So what kind of weather is possible? Pause the video and have a look at the trace. So what did you get? Well, we can see that the minus 20 degrees Celsius isotherm does cut through this profile towards the top of the cloud. So it is quite possible that we will get electrification, and a thunderstorm is possible for this trace. Here's Williamtown, and for 29 degrees Celsius and a dew point of 23 degrees, you can see there's definitely a convective condensation level. The surface lifting index is -8, and the CAPE is nearly 3,000 joules per kilogram. And so we can say quite confidently that the thunderstorm is very, very likely for this environment, and we might be worrying about things like strong winds at the surface and large hail because of the amount of CAPE providing a strong updraft to support hail. You can see, of course, too, that minus 20 degrees Celsius passes through this trace as well. A final example here from Perth. Is this convecting? Well, you can work out a convective condensation level, but where's the equilibrium level? About 1,000 feet above that. So this is also a convective environment, but because the convection is going to be capped by a strong inversion, this will be stratocumulus, which forms by the spreading out of a cumulus cloud. So convective environments come in all varieties, some producing thunderstorms, some only showers, and in this case probably just some stratocumulus cloud and no precipitation.